Right now, as you sit here watching this video, something vast and almost impossible to imagine is already on its way toward us. Not a meteor blazing through the atmosphere, not a comet slipping silently through the dark. What's approaching is far larger, far slower, and far more inevitable: an entire galaxy. The Andromeda galaxy, containing hundreds of billions, possibly a trillion stars, is drifting toward the Milky Way, pulled in by gravity over unimaginable distances, and in roughly 4 to 4.5 billion years, the two will meet. When they do, the night sky, the structure of our galaxy and our place within it, will be changed forever. Now, before that thought triggers panic, let's slow down and reset our intuition. A galactic collision is nothing like the word collision suggests in everyday life. There will be no single moment of impact, no blinding flash, no shockwave tearing through space. Galaxies are not solid objects. They are vast, delicate structures made mostly of empty space, with stars separated by distances so enormous that even during a merger, most stars will never come close to one another. If someone could somehow stand on Earth and watch the earliest stages of this event unfold, they might not notice anything unusual at all, at least not at first. And yet, over millions and then billions of years, everything will slowly, quietly transform. Spiral arms will stretch and unravel. New stars will ignite in brilliant bursts. Old orbits will be scrambled. Two great galactic systems will gradually lose their identities and become something entirely new. Tonight's journey is about understanding that transformation. We're going to start in the present, with what astronomers can observe right now. From there, we'll move forward through time, watching the long gravitational dance that leads to the first close pass, the repeated encounters, and finally, the complete merger. Along the way, we'll explore what happens to stars, to planets, to the Sun, and to Earth. Not in the language of equations and technical jargon, but as a story that unfolds across cosmic time. This is not a tale of sudden destruction. It's a story of scale, patience, and change. A form of time travel that spans billions of years, where the ticking clock is gravity itself. By the end, you won't just know that a galactic collision is coming. You'll understand what it truly means, why astronomers find it so fascinating, and how our quiet corner of the universe fits into one of the largest transformations it will ever experience. To understand what will eventually happen when two galaxies begin to merge, we first need to be very clear about what those galaxies actually are. It's tempting to think of a galaxy as a single object, like a planet or a star, but that intuition breaks down almost immediately when you look closer. Let's start at home with the Milky Way. From the inside, it feels vast and mysterious, but astronomers have spent decades piecing together its structure. The Milky Way is a barred spiral galaxy, which means it has a flat, rotating disk with sweeping spiral arms, and running through its center is a dense, elongated bar of stars. From this bar, the spiral arms unwind like a cosmic pinwheel, filled with gas clouds, dust lanes, and regions where new stars are constantly being born. At the very heart of this structure sits Sagittarius A, a supermassive black hole with a mass about 4 million times that of our Sun. Despite its fearsome reputation, this black hole is tiny compared to the galaxy itself. It governs the motions of stars very close to the center, but for most of the Milky Way, its influence is just one piece of a much larger gravitational puzzle. The galaxy as a whole stretches roughly 100,000 light-years from one side to the other. That number is easy to say, and almost impossible to truly feel. Light, the fastest thing in the universe, would need 100,000 years just to cross it. Within that enormous span live somewhere between 100 and 400 billion stars. The uncertainty isn't sloppiness, it's a reminder of perspective. Counting stars from inside a galaxy is like trying to count every tree in a forest while standing among the trunks, branches, and leaves. Dust blocks our view, distance blurs detail, and yet, even the lower estimate represents a population so large that the human brain struggles to hold it. Our Sun is one unremarkable star among these billions, orbiting the galactic center once every 225 million years, quietly embedded in one of the spiral arms. Now shift your attention outward, beyond the Milky Way, to its nearest large neighbor, the Andromeda Galaxy. From Earth today, Andromeda appears as a faint, fuzzy patch in the night sky, barely visible to the naked eye under dark conditions. That subtle glow hides something extraordinary. Andromeda is also a spiral galaxy, similar in overall shape to the Milky Way, but it is larger and more massive in nearly every respect. Its diameter spans roughly 220,000 light-years, more than twice the width of our own galaxy. Inside it are about 1 trillion stars, possibly more. That means for every star in the Milky Way, Andromeda may host 2 or 3. If Andromeda were placed where the Milky Way is now, its spiral arms would dominate our sky, stretching across a region many times wider than the full moon. At its center lies an even more massive black hole than ours, weighing tens or even hundreds of millions of solar masses, anchoring the motions of its densely packed core. Despite these differences in scale, the two galaxies share a deep kinship. Both formed more than 13 billion years ago, not long after the Big Bang, when the universe was young, smaller, and far denser than it is today. Both grew through the same process: gravity pulling together gas, dark matter, and smaller proto-galaxies, slowly assembling the elegant spiral structures we see now. And most importantly, both have spent their entire lives as members of the same gravitational family, the local group. The local group is a modest collection by cosmic standards, containing around 50 known galaxies. Most of them are small dwarf systems, faint and fragile, orbiting the two giants like moths around lanterns. From the very beginning, the Milky Way and Andromeda have been the dominant masses in this region of space, locked together by gravity across a gulf of millions of light-years. They have never been strangers drifting in from opposite sides of the universe. They were born in the same neighborhood, from the same cosmic web of matter, and have been slowly responding to each other's pull for over 13 billion years. This long companionship matters because it explains why what's coming is not an accident, but a continuation. The Milky Way and Andromeda are not on random trajectories. They are partners in a slow gravitational dance, circling, approaching, and shaping each other's futures long before the first stars of either galaxy had finished forming. When we talk about their eventual collision, we are not talking about two intact structures suddenly smashing together. We are talking about the gradual breakdown of these beautiful, organized systems, structures that took billions of years to assemble. That's why it's so important to picture them clearly now, while they still exist as recognizable spirals. The arms, the bars, the central bulges, the orderly rotations, all of this is temporary. Before we can appreciate what will be lost, reshaped, and reborn, we need to understand just how large, how complex, and how delicately balanced these galaxies are in their current form. Only then does the coming transformation carry its full weight. By this point, we've painted a clear picture of the two main characters in this story, the Milky Way and Andromeda, massive spiral galaxies that formed together, grew together, and have spent their entire existence bound within the same cosmic neighborhood. But describing their structures and shared history still leaves an obvious question hanging in the air. How do we actually know they are moving toward each other? How can astronomers be confident that this future collision isn't just speculation, a dramatic possibility rather than an unavoidable fate? The answer is where the story shifts decisively from imagination to measurement, from hypothesis to data. Astronomers don't rely on intuition when predicting events billions of years in the future. They rely on light. Every galaxy emits light from its stars, gas, and dust, and that light carries information about motion. When scientists analyze the light coming from the Andromeda galaxy, they aren't just seeing a distant glow, they're reading a kind of cosmic fingerprint. One of the most important pieces of information encoded in that light is something called radial velocity, which simply means how fast an object is moving toward us or away from us along our line of sight. Measuring radial velocity depends on a subtle but powerful effect. Light behaves a lot like sound in this regard. You've probably noticed that a siren sounds higher-pitched as it approaches and lower-pitched as it moves away. Light does the same thing, except instead of pitch, what changes is color. When a source of light moves toward us, its wavelengths are compressed slightly, shifting the light toward the blue end of the spectrum. When it moves away, the wavelengths stretch, shifting toward red. This shift is tiny, invisible to the naked eye, but it's easily detected with precise instruments. When astronomers carefully measured the spectrum of light from Andromeda, they found something remarkable. Instead of being redshifted, as most distant galaxies are due to the expansion of the universe, Andromeda's light is blue-shifted. That single observation carries enormous weight. It means Andromeda is not receding from us. It is approaching us. By measuring exactly how much the light is shifted, scientists can calculate the galaxy's speed with impressive accuracy. The result is about 110 kilometers per second, or roughly 250,000 miles per hour, directed almost straight toward the Milky Way. By everyday standards, that speed is astonishing. By cosmic standards, it's almost leisurely. Space is so vast that even at that velocity, it will take billions of years for the distance between the two galaxies to fully close. Still, the direction is unambiguous. The motion is real, measured, and repeatable. This isn't a one-off observation either. Multiple independent measurements, taken over decades with different instruments, all point to the same conclusion. Andromeda is coming toward us, and gravity is the reason why. Once that velocity is known, astronomers can do what they do best: run the clock forward. Using models that account for the masses of both galaxies, the distribution of dark matter around them, and the gravitational influence of smaller neighboring galaxies, scientists can simulate their future paths. These simulations don't produce a single exact date, because nature always allows some uncertainty. Small differences in mass estimates or initial velocities grow over billions of years. Instead, they produce a window of time. According to the best current data, the first major encounter between the Milky Way and Andromeda will begin roughly 3.5 to 5 billion years from now. That range might sound wide, but on cosmic timescales, it's remarkably precise. To put it in perspective, Earth itself is about 4.5 billion years old. The collision is not something vaguely predicted in the far future. It's scheduled on the same scale as the entire history of our planet. This is the moment where inevitability sets in. The galaxies are close enough, massive enough, and slow enough relative to each other that the expansion of the universe cannot pull them apart. Their mutual gravity has already won. Even if their exact paths wobble slightly due to interactions with smaller galaxies in the local group, the overall outcome doesn't change. They are bound together. They will meet. From here on, the question is no longer if a collision will happen, but how it will unfold. The data tells us that what began as a shared origin in the early universe has become a slow, unstoppable convergence. The measurements etched into Andromeda's light have transformed a distant possibility into a future certainty, setting the stage for the long, dramatic process that comes next. Once we accept that the Milky Way and Andromeda are truly on a collision course, another intuition immediately rebels. If two galaxies, each containing hundreds of billions of stars, are going to pass through each other, shouldn't that be catastrophically violent? Shouldn't stars smash together, worlds be torn apart, and space itself light up in destruction? This is where everyday intuition completely fails us, and where the reality of galaxy collisions turns out to be far stranger and far calmer than most people expect. The key lies in understanding just how empty a galaxy really is. When we look at images of spiral galaxies, they appear dense and luminous, their arms packed with stars. But that brightness is misleading. Stars are incredibly small compared to the distances that separate them. Even in relatively crowded regions like the disk of the Milky Way, the average distance between stars is measured in light years. Our nearest stellar neighbor is over 4 light years away, a gap so vast that light itself takes years to cross it. In that context, a galaxy is not a solid structure at all. It is more like a ghostly framework, held together by gravity, but composed almost entirely of empty space. This is why, when galaxies collide, individual stars almost never crash into one another. To make this counterintuitive idea easier to picture, astronomers often rely on analogies. Imagine 2 enormous swarms of bees flying directly toward each other. Thousands upon thousands of bees fill each swarm, buzzing in every direction. At first glance, it seems inevitable that collisions would be constant. But now, shrink each bee down to the size of a grain of sand and spread them out so that the average distance between grains is the length of a football field. When the 2 swarms pass through each other under those conditions, almost no grains ever touch. That's what a galactic collision is like. Stars are the grains of sand. The football field is the space between them. When the Milky Way and Andromeda overlap, their stars will mostly pass straight through, unaware that anything dramatic is happening on a personal scale. This fact alone dismantles one of the most persistent misconceptions about galaxy collisions. They are not explosive pileups of matter. They are not cosmic car crashes. But this does not mean they are gentle or insignificant. While stars rarely collide directly, they are still subject to gravity, and gravity does not need physical contact to wreak havoc. Every star exerts a gravitational pull on every other star. Normally, within a single spiral galaxy, these countless pulls balance out into a stable pattern. Stars follow relatively orderly orbits around the galactic center, maintaining the familiar spiral structure for billions of years. A collision changes that balance. When 2 galaxies interpenetrate, their gravitational fields overlap. Suddenly, stars are no longer responding to a single, smooth gravitational environment, but to a shifting, uneven one, created by 2 massive systems pulling at once. This is where chaos enters the picture. A star that once followed a calm, nearly circular orbit may find itself tugged in a new direction. Over time, that small nudge grows. Orbits stretch, tilt, and warp. Some stars are thrown onto elongated paths that carry them far from where they were born. Others gain so much energy from repeated gravitational interactions that they are flung completely free, ejected into the vast intergalactic void, destined to wander alone between galaxies for the rest of cosmic time. These stars are not destroyed, but they are exiled, stripped of their original home by gravity alone. While stars behave like ghosts passing through one another, gas and dust tell a very different story. Unlike stars, clouds of gas do collide. They slam together, compress, and heat up as the galaxies overlap. These clouds are the raw material of star formation, and when they are squeezed by gravitational forces, something spectacular happens. Regions of gas collapse under their own weight, igniting waves of new star birth. Entire clusters of hot, massive stars flare into existence, lighting up the merging galaxies with brilliant blue light. This process can dramatically increase the rate at which stars form, sometimes by 10 or even 100 times compared to a quiet, isolated galaxy. Ironically, while galaxy collisions feel destructive in concept, they are often intensely creative events. They tear apart old structures, but in doing so, they trigger the birth of countless new stars. Dust lanes twist and buckle. Nebulas glow. Supernovae soon follow as the most massive of these newborn stars burn through their fuel and explode. From the outside, a merging pair of galaxies can appear more luminous and more active than they ever were before. This dual nature is essential to understand. A galaxy collision does not annihilate its participants. It transforms them. Order gives way to disorder. Flat disks puff up into thicker, more chaotic shapes. Graceful spiral arms stretch and dissolve. Yet at the same time, new stars blaze into existence, seeded by the very chaos that destroyed the old patterns. What emerges from a collision is not ruin, but reinvention. By letting go of the idea of galaxies as solid objects and embracing their true nature as vast, delicate systems governed by gravity, we can finally grasp what is really coming. The future collision between the Milky Way and Andromeda is not a moment of sudden destruction. It is a long, intricate process of transformation, one that reshapes structure, redistributes stars, and sets the stage for a galaxy unlike either of its parents. Once we understand that galaxy collisions reshape rather than obliterate, the next realization follows naturally. This upcoming merger is not a first-time experiment. Both of the galaxies involved have been rehearsing for this moment for most of their lives. Long before the Milky Way and Andromeda ever meet each other directly, they have each been quietly growing by swallowing smaller neighbors. In fact, this process of gradual consumption is one of the primary ways large galaxies evolve at all. Take the Andromeda Galaxy. When astronomers study its outer regions in detail, they find that it is surrounded by faint, ghostly structures, long streams of stars, arcs, and shell-like features that don't fit neatly into a smooth spiral pattern. These are not random decorations. They are the stretched-out remains of dwarf galaxies that once orbited Andromeda too closely. Over time, Andromeda's gravity pulled them apart, peeling off their stars and smearing them across space like cosmic fingerprints. Each stream tells the story of a smaller galaxy that was gradually torn to pieces and absorbed, its individual identity erased, its stars folded into Andromeda's larger structure. In a very real sense, Andromeda is already a composite object, built from many earlier mergers layered on top of one another, The same story is playing out closer to home. The Milky Way is not a passive observer in this cosmic process. Right now, as you watch this video, our galaxy is in the middle of dismantling the Sagittarius dwarf galaxy. This small companion galaxy is on a looping orbit around the Milky Way, and with each pass, it is stretched thinner. Its stars are being pulled away and spread into enormous stellar streams that wrap all the way around our galaxy. These streams are so extensive that they form a kind of luminous ribbon threading through the Milky Way's halo. Eventually, the Sagittarius dwarf will cease to exist as a distinct galaxy at all. Its stars will become just another part of the Milky Way's vast stellar population, indistinguishable from those that formed here billions of years ago. This is not violence in the explosive sense. It is slow, methodical erosion driven by gravity. And it's happening everywhere in the universe. Large galaxies grow by consuming smaller ones, leaving behind these telltale stellar streams and shells as archaeological evidence of past encounters. When astronomers find such structures, they are not speculating about ancient collisions. They are reading the fossil record of galactic evolution. This perspective is crucial. The future merger between the Milky Way and Andromeda is not some rare cosmic anomaly. It is simply the largest and most dramatic version of a process both galaxies already know well. By the time the slow convergence we've been describing reaches its most dramatic stages, the universe itself will already feel unfamiliar. Roughly 4 billion years from now, long before the first stars from the Andromeda galaxy ever pass through the disk of the Milky Way, the Phytotherians will have undergone changes far more profound than anything caused by a galactic merger. The Sun, aging steadily and inexorably, will be significantly brighter than it is today. That extra energy will have pushed Earth beyond the delicate balance that allows liquid water to exist on its surface. Oceans may have evaporated or retreated into isolated remnants. The climate, once moderated by clouds and seas, may have tipped into a runaway greenhouse state. If life ever arose here, it is unlikely to remain on the surface. Any intelligent descendants of humanity, if they exist at all, will almost certainly have moved elsewhere, abandoning Earth as a relic world orbiting a star that has grown too intense for comfort. And yet, even as Earth itself fades as a living home, the sky above it, or above whatever outposts or habitats now circle the Sun, will be entering a phase of breathtaking transformation. For millions of years leading up to this era, observers would have noticed a slow but undeniable change. Andromeda, once a faint smudge barely visible under dark skies, would have grown steadily larger. Not in a way noticeable from one night to the next, or even from one generation to the next, but unmistakable when viewed across geological timescales. Ancient records compared to modern skies would show the difference clearly. The fuzzy patch would stretch wider, its central glow brighter, its structure gradually resolving into something unmistakably galactic. Spiral arms would begin to reveal themselves without the aid of telescopes, pale arcs of light curving across the darkness. By 4 billion years in the future, Andromeda would dominate the night sky. It would no longer be a curiosity tucked between constellations, but a massive presence, sprawling across a significant fraction of the heavens. Its bright central bulge would cast a soft glow, and its sweeping arms, dotted with clusters of young blue stars, would be visible as ghostly bands. The sky would feel crowded in a way no human has ever experienced. Stars would seem denser. The sense of depth and scale would be overwhelming, as if the universe itself had leaned closer. From an observational standpoint, This would be the first unmistakable sign that the long-anticipated encounter was truly underway. But the most important changes would not be limited to appearance alone. Even while the galaxies remain millions of light-years apart, gravity would already be at work, quietly distorting both systems. The earliest physical evidence of this influence would appear in their outer regions. Astronomers would detect subtle asymmetries in the distribution of stars near the edges of each galaxy. Faint streams would begin to stretch outward, barely visible against the background darkness. These are tidal tails, and they are among the clearest signatures that a galactic interaction has begun. Tidal tails form for the same reason oceans rise and fall on Earth. Gravity exerts a stronger pull on the near side of an object than on the far side, creating a stretching force. In the case of galaxies, this stretching acts on stars and gas instead of water. The stars on the side of the Milky Way, closest to Andromeda, feel a slightly stronger gravitational tug than those on the far side. Over time, that difference adds up. Stars are drawn outward, forming long, elegant streams that arc away from the main disk. Andromeda experiences the same effect, its own stars being teased out into vast, luminous tendrils. At first, these tidal features would be subtle, detectable only with careful observation and sensitive instruments. But as millions of years pass, they would grow longer and more pronounced, stretching tens and then hundreds of thousands of light-years into space. From a cinematic perspective, this period is one of slow revelation rather than sudden drama. Nothing explodes. Nothing collapses overnight. Instead, the galaxies begin to look slightly wrong, as if their familiar symmetry has been gently disturbed. Spiral arms lose their perfect balance. The outer edges appear frayed. The sky tells a story of tension building, of forces accumulating toward an inevitable release. Inside the Milky Way, daily life, whatever form it takes for future observers, would still feel remarkably normal. Stars continue their long orbits around the galactic center. The Sun traces its path, completing one circuit every few 100 million years. There are no earthquakes in space, no immediate disasters announcing the coming merger. Yet, with long-term monitoring, astronomers would notice that stellar orbits are no longer perfectly predictable. Tiny deviations appear. A star's path becomes slightly more elongated, slightly tilted. Individually, these changes are insignificant. Collectively, they are the first hints that the galaxy's internal order is beginning to loosen. The gas between the stars responds even more dramatically. As Andromeda's gravity reaches out, vast clouds of gas in the Milky Way are gently compressed in some regions and stretched thin in others. In the compressed zones, conditions become ripe for star formation. New stars ignite in clusters, their intense blue light announcing their birth. These regions would glow brightly, marking the places where gravity is beginning to reshape the galaxy from within. To an observer watching the sky over millions of years, these changes would feel like watching a slow-motion storm gather. The clouds thicken. The winds shift. The first flashes of lightning appear on the horizon. The appearance of tidal tails and enhanced star formation is the universe's way of signaling that the collision has already begun, even if the galaxies have not yet passed through one another. This phase transforms the night sky into a living record of gravitational interaction. The heavens would no longer look static or eternal. They would feel active, dynamic, evolving. Andromeda's presence would serve as a constant reminder that the cosmos is not frozen in place. It moves, it changes, and it carries everything within it along for the ride. By shifting our perspective to that of an observer living through this era, we begin to grasp the true scale of what's unfolding. The merger is not a single event waiting in the distant future. It is a process already in motion, written into the changing patterns of light across the sky, unfolding patiently over billions of years, transforming the familiar into something vast, strange, and profoundly beautiful. As the slow gravitational tension between the two galaxies continues to build, the story reaches its first true physical climax. Up to this point, the changes have been subtle. Stretched stars, distorted edges, graceful tidal tails reaching into darkness. But now, gravity begins to act not just on structure, but on matter itself. The vast reservoirs of gas that once drifted calmly within the disks of the Milky Way and the Andromeda galaxy are no longer left undisturbed. They are squeezed, shocked, and forced into conditions they have not experienced since the galaxies were young. This is the moment astronomers call a starburst, and despite the name, it is not a single explosion, but a sustained, violent renaissance of creation. Gas is normally reluctant to form stars. Even in calm galaxies like the Milky Way today, only a small fraction of available gas ever collapses into new suns. Gravity must overcome internal pressure, turbulence, magnetic fields, and heat. But during a galactic encounter, those safeguards weaken. As the two galaxies pass close enough for their gravitational fields to overlap deeply, enormous clouds of hydrogen are compressed like cosmic bellows. Streams of gas collide at hundreds of kilometers per second. Shock waves ripple through the interstellar medium, stripping away energy and allowing gravity to finally take control. Regions that were once stable for billions of years suddenly collapse. One cloud fragments into thousands of dense knots. Each knot continues to contract, growing hotter and denser until nuclear fusion ignites at its core. A star is born, and then another, and another. Entire stellar nurseries light up across both galaxies almost simultaneously. From the outside, this phase is unmistakable. The galaxies brighten dramatically, especially in blue and ultraviolet light. That color shift is a signature of youth. The stars forming during a starburst are not gentle, sun-like stars that burn quietly for billions of years. They are massive, hot, and short-lived. Many are 10, 20, or even 100 times more massive than the Sun. Their surfaces blaze at tens of thousands of degrees, flooding their surroundings with intense radiation. They burn through their fuel at an incredible pace, living fast and dying young on cosmic timescales. Instead of billions of years, they survive for only a few million. In the life of a galaxy, that is barely a heartbeat. But while they live, they dominate everything around them. Their ultraviolet radiation carves glowing bubbles into surrounding gas clouds. Their powerful stellar winds sweep material outward, compressing some regions while evacuating others. These massive stars reshape their neighborhoods almost as violently as the collision that created them. And then, just as quickly as they appeared, they begin to die. When a massive star runs out of fuel, gravity wins in an instant. The core collapses, rebounds, and the star tears itself apart in a supernova explosion. Each of these detonations releases more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. During the starburst phase, supernovae are no longer rare, isolated events. They become common. Across the merging galaxies, explosions erupt again and again, lighting up the darkness with brief, catastrophic flashes. These supernovae enrich the surrounding gas with heavy elements, scattering iron, oxygen, carbon, and countless other elements forged in stellar cores. This chemical enrichment is one of the paradoxes of galactic violence. The same explosions that destroy stars also provide the raw materials needed for planets and life. Yet the immediate environment during a starburst is anything but friendly. Radiation levels rise dramatically. Ultraviolet light from massive stars strips electrons from atoms, heating and ionizing the gas. X-rays and gamma rays from supernova remnants permeate large volumes of space. For planets caught nearby, this radiation can be devastating. If life exists on any world close to these regions, its protective atmosphere becomes its last line of defense. Strong radiation can erode atmospheres, damage ozone layers, and expose planetary surfaces to lethal doses of energy. On Earth today, we are shielded by distance and by the relatively calm state of our galaxy. During a starburst, that safety margin shrinks. The risk is not limited to radiation alone. The shock waves from repeated supernovae stir the interstellar medium into a turbulent frenzy. Gas clouds slam into one another, generating further compression and triggering yet more star formation in a cascading cycle. Astronomers sometimes describe this as feedback. Stars are born, they disrupt their surroundings, and in doing so, they both create and destroy the conditions for future stars. At first, feedback accelerates the starburst. Later, it begins to choke it off. As more explosions occur, the gas becomes too hot and too chaotic to collapse further. Eventually, enormous amounts of gas are blown out of the galaxies entirely, streaming into intergalactic space in vast galactic winds. These winds mark the beginning of the end for the starburst. But before that happens, the rate of star formation reaches extraordinary heights. Where a calm galaxy might form 1 or 2 stars per year, a starburst galaxy can form dozens or even hundreds. The night sky, if observed from within, would be unrecognizable. New stars would appear in clusters, glowing intensely blue-white. Nebulas would blaze in vivid colors, illuminated from within by newborn suns. The galaxy would feel alive, restless, and unstable. For any civilization living through this era, the implications are profound. The increased radiation makes certain regions hazardous or outright uninhabitable. Worlds that once enjoyed stable conditions may face atmospheric loss or repeated extinction events driven by nearby supernovae. At the same time, entirely new planetary systems are forming around young stars, seeded with heavy elements and bathed in energy. Some of these worlds may be hostile, scorched by radiation. Others, farther from the chaos, may eventually cool and stabilize, offering fresh environments where life could arise. This duality lies at the heart of the starburst. It is both a destroyer and a creator. It raises the stakes for every existing biosphere, increasing the risk of extinction, while simultaneously expanding the number of places where life might one day begin. From a physical standpoint, this phase represents the most dramatic transformation yet. The orderly balance of the galaxies has fully collapsed. Gravity has crossed a threshold, turning slow distortion into runaway change. The collision is no longer a distant future event, hinted at by stretched stars and tidal tails. It is happening now, written in fire across the galaxies. And as the starburst rages, it becomes impossible to ignore a sobering truth. The survival of planets and the fate of life are no longer governed solely by the quiet stability of their stars. They are now tied directly to the violent heartbeat of a galaxy in collision, where creation and destruction unfold side by side on a scale that dwarfs anything a single world could ever control. As the starburst phase reshapes the galaxies on vast scales, it's natural for attention to narrow toward something far more personal. Amid all this cosmic upheaval, What happens to our own neighborhood? What becomes of the solar system, of Earth, of the familiar clockwork of planets that has remained stable for billions of years? This is the question most people carry quietly through every discussion of galaxy collisions, and it deserves an answer grounded in real physics rather than cinematic fear. The surprising truth is that, in many ways, the solar system is far more resilient than intuition suggests. Even during a major galactic merger, the chance that another star will pass close enough to directly disrupt the Sun and its planets is remarkably small. Space remains overwhelmingly empty, even when two galaxies overlap. Stars do not crowd together like grains in a sand pile. They pass through one another's territories, separated by distances measured in light years. For a passing star to significantly alter the orbits of the planets, it would need to come within roughly a light year of the Sun, and preferably much closer. Encounters that tight are rare, even during the most chaotic stages of a merger. Most stars, including our own, will drift through the collision without ever experiencing such an intimate gravitational handshake. This alone strips away a great deal of the drama often associated with the idea of a galactic collision. The solar system is not likely to be torn apart by a rogue star sweeping through and scattering the planets like billiard balls. The inner planets, especially Earth, are bound tightly to the Sun. Their orbits are deep gravitational wells, difficult to disturb from the outside. If danger comes, it will arrive more subtly, from farther out. Beyond the orbit of Neptune lies a vast, almost invisible structure that rarely enters popular imagination. A distant halo of icy debris left over from the formation of the solar system. These objects are only loosely held by the Sun's gravity, balanced delicately between our star and the gravitational influence of the galaxy itself. Under normal circumstances, this region is quiet. A few comets are nudged inward every million years or so, occasionally lighting up our skies. During a galactic merger, that balance is disturbed. As nearby stars pass at distances of a few light years, their gravity can tug at this distant reservoir. Each encounter sends ripples through it, knocking some icy bodies onto new trajectories. Many are lost to interstellar space entirely. Others are redirected inward, toward the heart of the solar system. The result is a comet shower, not a single dramatic impact, but a prolonged period of increased bombardment lasting millions of years. For any planet with a surface and a history of life, this matters. Large comet impacts can alter climates, trigger mass extinctions, and reshape planetary surfaces. Earth itself bears the scars of such events. During a merger, the frequency of these impacts could rise significantly. Not enough to guarantee destruction, but enough to raise the background risk, turning what was once rare into something more persistent. This is one of the most plausible ways the merger could directly affect life on planets like Earth. Not through stars colliding, but through a slow rain of icy debris stirred up by distant gravitational encounters. Radiation presents another concern. The starburst phase floods parts of the galaxy with energetic light. Massive stars pour out ultraviolet radiation, and their deaths as supernovae unleash bursts of X-rays and gamma rays. A single nearby supernova can be dangerous. If one occurs within a few dozen light years of a planet like Earth, it has the potential to damage the atmosphere, deplete ozone, and expose the surface to harmful radiation. During the merger, the overall rate of supernovae increases, especially in regions dense with new star formation. This raises the odds, but it's important to keep perspective. Even in a starburst, space is vast. Supernovae are still separated by enormous distances, The probability that one will occur close enough to Earth to cause severe harm remains low. Elevated, yes. Inevitable, no. The galaxy becomes a more hazardous place, but not uniformly deadly. Some regions are far more dangerous than others, and much depends on where the solar system happens to be at the time. Yet for all this talk of external threats, none of them represent the most certain end awaiting Earth. The real death sentence does not come from the collision at all. It comes from the Sun itself. Long before the Milky Way and Andromeda complete their merger, the Sun will have changed Earth beyond recognition. As stars age, they brighten. This process is slow, but relentless. Over the next billion years, the Sun's increasing luminosity will push Earth out of the narrow temperature range that allows liquid water to exist on its surface. Oceans will evaporate. Weather will collapse into extremes. The planet will likely enter a runaway greenhouse state, becoming hot, dry, and hostile. This transformation is independent of any galactic event. It is written into stellar physics. By the time the galaxies are deeply intertwined, Earth will almost certainly be lifeless, at least on its surface. Even if the solar system survives the merger intact, even if no nearby supernova ever flashes close enough to matter, Earth's fate is already sealed by the simple passage of time. This realization is oddly calming. It strips away the temptation to dramatize the galaxy collision as a sudden cosmic apocalypse for our world. The merger is not what kills Earth. Earth will be gone as a living world long before the merger reaches its most intense stages. For any future observers descended from humanity, survival would depend not on avoiding galactic catastrophe, but on having left Earth behind. In that sense, the galaxy collision becomes almost irrelevant to our immediate story. It is a backdrop, not the executioner. The solar system may drift into a new orbit. The night sky may transform beyond recognition. Comets may fall more frequently, and radiation may rise and fall with waves of star formation. But the dominant force shaping Earth's destiny is local and familiar. A single aging star at the center of our planetary family. By grounding the story here, the drama becomes quieter but more honest. The universe does not single us out for destruction. It simply moves forward, following laws that apply everywhere to everything. The collision of galaxies is one of those grand processes, vast and indifferent. Earth's end comes not with a bang from the heavens, but with a slow warming, a brightening sun, and the inexorable ticking of stellar time. As the chaos of starbursts, radiation, and orbital reshuffling slowly subsides, attention shifts inward, toward the deepest gravity wells of both galaxies. Long after spiral arms have been stretched and stellar populations mixed, the most consequential encounter still lies ahead. At the center of the Milky Way resides Sagittarius A, a supermassive black hole with a mass of about 4 million suns. At the heart of the Andromeda galaxy lurks an even larger one, weighing tens to hundreds of millions of solar masses. For billions of years, each of these objects has quietly anchored its own galaxy, shaping stellar motions without ever revealing itself directly. Now, as the merger progresses, these two invisible giants are destined to meet. But even here, intuition misleads. Black holes do not rush toward each other in a dramatic plunge the moment the galaxies overlap. They are carried along by the massive stellar cores surrounding them. As the galaxies pass through one another for the first time, the black holes remain separated by tens of thousands of light years, embedded in dense swarms of stars. Gravity begins the long work of bringing them together through a process known as dynamical friction. As each black hole moves through the sea of stars and dark matter in the merged system, it gravitationally tugs on nearby material. Those stars are slightly accelerated, stealing energy and momentum from the black hole. Over millions of years, this subtle exchange slows the black holes down, causing them to spiral inward toward the center of the newly forming galaxy. This inward migration is slow, methodical, and relentless. Eventually, the two black holes find themselves bound together in a shared orbit, forming what astronomers call a binary supermassive black hole system. Two objects of extraordinary mass, separated by a distance that shrinks steadily over time, circling a common center of gravity. This phase alone can last hundreds of millions of years. During it, the surrounding region becomes one of the most extreme environments in the universe. Stars passing too close can be flung outward at tremendous speeds or torn apart entirely, their matter stretched into glowing streams before being consumed. Gas clouds drawn toward the pair are heated to incredible temperatures, forming luminous accretion disks that can briefly cause the galactic core to blaze across vast distances. Yet even in this violence, something remarkable happens. The most powerful signal produced by this system is not light. It is motion itself, written into the fabric of space-time. As the two black holes orbit each other, they accelerate. And according to Einstein's theory of general relativity, accelerating masses generate gravitational waves. These waves are ripples in space-time that propagate outward at the speed of light, carrying energy away from the system. Unlike light, they pass almost unhindered through matter, traveling across the universe as pristine messengers of extreme events. This is where the story of the Milky Way Andromeda merger connects directly to modern physics. Over the past decade, humanity has learned how to detect gravitational waves from the mergers of much smaller black holes, each only a few dozen times the mass of the Sun. But a supermassive black hole merger is a different beast entirely. The waves it produces are far lower in frequency, stretching and squeezing space-time over periods of hours or even days. They are too slow for ground-based detectors to sense. Instead, future space-based observatories like the planned Laser Interferometer space antenna are designed specifically to listen for these cosmic vibrations. When the central black holes of the Milky Way and Andromeda finally draw close enough, they will become one of the loudest gravitational wave sources the local universe has ever known. For any civilization capable of detecting these signals, the event would be unmistakable. The waves would rise steadily in strength as the orbit tightens, a deep, rhythmic pulse echoing through space-time itself. This broadcast would carry detailed information about the masses of the black holes, their spins, and the geometry of their orbit. It would be a masterclass in gravity, unfolding in real time, confirming predictions made centuries earlier by theory alone. And then, at last, the final moments arrive. As the black holes draw within a few light hours of each other, gravitational wave emission accelerates dramatically. The orbit shrinks from light years to light minutes, then to light seconds. The final merger happens astonishingly fast. In a fraction of a second, the two horizons fuse into one. The result is a single supermassive black hole with a mass of roughly 100 million suns, slightly less than the combined mass of its progenitors, because a small fraction has been converted directly into gravitational wave energy. This is the most powerful release of energy since the Big Bang itself. And yet, to any observer relying on light, almost nothing appears to happen. There is no universal flash, no galaxy-spanning explosion. Black holes merging do not produce fireworks. The energy is carried away silently, invisibly, through space-time. The night sky does not suddenly blaze brighter. The universe does not announce the moment with spectacle. The merger is dramatic only to those who know how to listen. After the merger, the newborn black hole may not remain perfectly centered. If the gravitational waves were emitted asymmetrically, the black hole can receive a recoil, a gravitational kick that sends it drifting through the core of the new galaxy at hundreds or even thousands of kilometers per second. Over time, dynamical friction once again does its work, drawing it back toward the center, where it will settle as the ultimate anchor of the merged system. From that point on, the black hole resumes its quiet role, influencing stars only through gravity, largely invisible except when fed by infalling gas. This final dance marks the true climax of the merger, not because it is visually dramatic, but because it represents the convergence of everything we understand about gravity, motion, and cosmic evolution. Two galaxies collide. Their stars pass like ghosts. Their gas ignites into storms of creation. Their planets endure or perish according to local chance. And at the very center, the most extreme objects known to physics spiral together, broadcasting their union across the universe in ripples of spacetime. It is a moment where abstract equations become reality, where predictions written on chalkboards are played out on scales beyond comprehension. When the Milky Way and Andromeda finally become one, the merger of their central black holes will not light up the sky. It will quietly rewrite the gravitational story of the region forever, leaving behind a single, deeper well of space-time curvature at the heart of a new galaxy, a silent monument to the power of gravity acting patiently across billions of years. With the final merger of the central black holes complete, the last echoes of gravitational waves fading into the cosmic background, the long transformation finally settles into something stable. The chaos that once defined the collision gradually gives way to equilibrium. What remains is no longer the Milky Way. It is no longer Andromeda. What exists now is a single, unified galaxy, often nicknamed Milkdromeda or Milomeda, a name that hints at its dual heritage, but also at the fact that something entirely new has been born. From a structural perspective, this new galaxy looks nothing like its parents did in their youth. The elegant spiral arms that once defined both galaxies are gone. They have been stretched, shredded, and erased by billions of years of gravitational turbulence. In their place is an elliptical galaxy, a vast rounded swarm of stars with no clear disk, no organized rotation, and no grand pinwheel pattern crossing the sky. Stars now move on random three-dimensional orbits, plunging in elongated paths through the galactic core and out into the halo, held together only by the combined gravity of trillions of suns and the enormous dark matter halo surrounding them. This outcome is not unusual. Astronomers see elliptical galaxies everywhere in the universe, especially in dense environments like galaxy clusters. For decades, observations and simulations have pointed to the same conclusion. When two large spiral galaxies merge, the result is almost always an elliptical galaxy. The ordered rotation that supports spiral arms is fragile. Once disrupted by another galaxy of comparable mass, it never fully recovers. Milkdromeda is the natural end state of that process. At its center lies the newly merged supermassive black hole, weighing on the order of 100 million solar masses. Despite its size, it occupies an almost vanishingly small volume compared to the galaxy itself. Most stars will never come anywhere near it. From the outside, it is invisible. From the inside, it is simply the deepest point in a vast gravitational landscape, quietly anchoring the motions of everything else. Surrounding it is a dense central bulge where stars are packed more tightly, gradually thinning into a broad halo that extends hundreds of thousands of light years into space. One of the most important differences between this new galaxy and its spiral ancestors is the state of its gas. During the merger, enormous amounts of gas were consumed in starbursts or blown out by supernova-driven winds. What remains is hot, diffuse, and difficult to collapse. Without cold, dense gas, star formation slows to a crawl. Milkdromeda is no longer a prolific stellar nursery. It is a galaxy entering middle age, dominated by stars that formed long ago. A few new stars may still appear from time to time, but the era of dramatic creation is over. This shift has profound consequences for how the galaxy looks from the inside. In the Milky Way today, the night sky is shaped by our position inside a disk. We see a bright band, the Milky Way itself, arching overhead, marking the dense plain of stars and dust. In an elliptical galaxy, that geometry disappears. There is no disk, no single plane where stars are concentrated. Instead, stars surround observers in all directions. The sky becomes more uniform, filled with points of light across every angle. The sense of orientation changes completely. There is no up toward the galactic plane, no sweeping band to serve as a cosmic landmark. The stars are everywhere. Their colors, too, tell a different story. Without ongoing star formation, the bright blue stars that once dominated starburst regions gradually vanish. Massive stars live fast and die young, exploding as supernovae within a few million years. Over billions of years, they disappear entirely. What remains are long-lived, lower-mass stars, yellow suns, orange dwarfs, and vast numbers of small red stars burning their fuel slowly and quietly. The galaxy's overall light shifts toward red and amber hues. From a distance, Milkdromeda would appear smoother and dimmer than its parents once did, lacking the sharp contrast of spiral arms and glowing nebulae. For any planetary systems that survive into this era, the sky would feel calmer, older, and more subdued. There would be fewer supernovae lighting up the darkness, fewer violent outbursts of radiation. The galaxy would feel stable in a deep, time-worn way. Yet this calm is not the same as youth. It is the quiet that follows exhaustion. The raw material for new beginnings has largely been used up. The galaxy now lives off its inheritance. Over time, subtle relics of the merger remain visible. Even billions of years later, astronomers could detect faint shells, ripples, and streams of stars in the outer halo, echoes of the violent past preserved in slow-moving orbits. These structures are like wrinkles in spacetime's fabric, reminders that this smooth elliptical form was once two separate, dynamic spirals. Eventually, even these features fade as stellar orbits mix and relax. The galaxy becomes increasingly uniform, increasingly featureless, increasingly ancient. On the largest scale, Milkdromeda is not alone, but it is increasingly isolated. As dark energy continues to drive the accelerated expansion of the universe, galaxies beyond the local group slip away, their light stretched and redshifted beyond detectability. In the far future, Milkdromeda and a handful of small satellite galaxies may be all that remains visible. To observers living then, the universe would appear vastly smaller than it does to us today. The cosmic web of galaxies would be gone from view. The grand architecture of the universe would be hidden beyond an unreachable horizon. In that sense, Milkdromeda is both a culmination and a closing chapter. It represents the final major act of galactic assembly in our region of space. The Milky Way and Andromeda grew for billions of years by consuming smaller galaxies. Eventually, they met each other. After that, there is little left to merge with. Gravity has done its consolidating work. What remains is a single, massive system slowly aging in an expanding universe. From a storytelling perspective, this is the resolution the narrative has been building toward all along. The collision did not end in fire or annihilation. It ended in transformation. Order gave way to chaos, chaos to renewal, and renewal to stability. The galaxy we call home was never meant to be permanent. It was always a temporary configuration of matter, shaped by gravity and time, destined to change. Milkdromeda is not a failure of that story. It is its continuation. And within that final shape lies a quiet truth. Galaxies, like stars and planets and living things, have life cycles. They are born, they grow, they interact, and they age. The spiral arms that seem so timeless to us are fleeting on cosmic timescales. The night sky we know is a snapshot, not a constant. One day, long after humanity's chapter has ended or transformed beyond recognition, the stars will still shine. But they will do so from a galaxy that no longer remembers being two. Milkdromeda will drift through an ever emptier universe, a vast elliptical city of aging suns, carrying within it the blended histories of countless stars, worlds, and vanished structures. That is the final shape of the collision, not destruction, but inheritance. A single galaxy bearing the accumulated memory of billions of years, moving quietly through a cosmos that continues to expand, indifferent yet astonishing, long after the last spiral arm has faded from the sky. As Milkdromeda settles into its final elliptical form, the most dramatic chapters of galactic interaction are over. The stars have mixed, the gas has been largely spent or expelled, and the once familiar structures of spiral arms exist only as memories written into ancient stellar orbits. On the scale of individual galaxies, the story feels complete. But on the scale of the universe itself, another, quieter transformation is unfolding. One that will shape the experience of any observer who exists far into the future. This transformation has nothing to do with collisions or gravity pulling things together. It has everything to do with something far more subtle and far more powerful: the accelerated expansion of space itself. The universe is not just expanding, it is expanding faster and faster, driven by a mysterious component of reality we call dark energy. While gravity works to draw matter inward, dark energy stretches space outward, and on the largest scales, it wins. Over billions and then trillions of years, this expansion steadily carries distant galaxies away from one another, increasing the space between them until even light can no longer bridge the gap. Today, when we look into the night sky with powerful telescopes, we see hundreds of billions of galaxies scattered across the observable universe. They form clusters, filaments, and vast walls surrounding enormous voids. This cosmic web gives us a sense of belonging to something immense and interconnected. But this view is temporary. The expansion of the universe ensures that it cannot last. As time passes, galaxies that are not gravitationally bound to us will recede faster and faster. Their light will be stretched to longer wavelengths, dimmed, and eventually redshifted beyond detectability. One by one, they will slip from view, not because they have vanished, but because the expanding fabric of space has carried them beyond our cosmic horizon. In the distant future, observers living within Milkdromeda will inhabit a very different universe from the one we know. The local group, once a modest collection of dozens of galaxies, will have consolidated almost entirely into a single dominant system. Small satellite galaxies may still orbit Andromeda, remnants of the original group, but everything beyond that will be gone from sight. The Virgo cluster, once the nearest great congregation of galaxies, will fade away. More distant clusters will disappear even sooner. Over time, the sky will empty. What was once a deep, layered vista of galaxies at every distance will collapse into a lonely scene dominated by a single massive galaxy and its immediate surroundings. To an observer born into that era, this emptiness would feel natural. Andromeda would appear to be the entire universe. The sky would be filled with stars, but beyond them, darkness would reign. No faint smudges of distant galaxies would mark the depths of space. No evidence of a larger cosmic structure would be visible. The universe would feel small, static, and self-contained. Without records, without inherited knowledge, such observers might reasonably conclude that their galaxy is all there is. The idea of a vast universe teeming with galaxies could seem speculative or even absurd. This is what it means for the universe to become consciously isolated. Not isolated in a physical sense. Other galaxies still exist, far beyond reach, but isolated in terms of perception and knowledge. The observable universe shrinks, not because space collapses, but because it stretches too quickly for information to keep up. Light emitted by distant galaxies will never reach Andromeda again. No signal sent outward will ever be answered. The universe becomes a place where contact is no longer possible, even in principle. This isolation carries deep philosophical weight. Today, we live in a privileged era. We can see the cosmic microwave background, the afterglow of the Big Bang itself. We can map galaxies across billions of light years. We can reconstruct the history of the universe with remarkable precision. Future observers will not have that luxury. The evidence will be gone, erased not by destruction, but by expansion. Even the cosmic microwave background will eventually redshift into wavelengths so long that it blends indistinguishably with the cold noise of space-time. The universe's origin will be hidden behind an observational veil. For those who come later, cosmology will be an exercise in inference with almost no data. This loss is not violent or dramatic. It happens slowly, gently, over unimaginable spans of time. There is no moment when the universe suddenly goes dark. Instead, there is a gradual thinning, a fading of distant lights, a steady retreat of the horizon. Each generation would notice nothing unusual. Only by comparing records across billions of years would the change become apparent. This is part of what makes the future universe so haunting. The sadness is not sharp, it is diffuse. It is the quiet sadness of something vast slipping away unnoticed. And yet, there is beauty here as well. Within Andromeda, stars will continue to shine for trillions of years. Red dwarfs, the most common and longest-lived stars in the universe, will burn slowly and steadily, providing stable energy for unimaginable lengths of time. Planetary systems may persist long after the last spiral arm has faded from memory. Life, if it arises or endures elsewhere, could still flourish in pockets, unaware of the wider universe that once existed beyond reach. From this perspective, the universe does not end. It contracts inward in experience, focusing everything into smaller and smaller islands of matter, surrounded by an ever-growing sea of emptiness. Andromeda becomes one such island, a self-contained cosmos drifting through accelerating space. Its stars carry the combined history of two galaxies, and within them, the chemical record of countless earlier generations of stars. Everything that can be known is contained there, and everything beyond becomes forever unknowable. This raises a striking contrast between past, present, and future. In the distant past, shortly after the Big Bang, the universe was hot, dense, and nearly uniform. In the present, it is rich, structured, and vast, filled with galaxies and light. In the distant future, it becomes sparse, isolated, and quiet. Not empty, but lonely. Not dead, but withdrawn. The arc of cosmic history bends from unity to diversity, and then from diversity to isolation. Standing at the midpoint of that arc, we are uniquely positioned to see both where the universe came from and where it is going. The observers of the far future will see only the destination. There is something deeply poetic about this progression. The Milky Way and Andromeda merged not to create chaos, but to ensure continuity. As the universe expands and fragments into unreachable regions, gravity gathers what it can, preserving complexity in small pockets. Milkdromeda is one such pocket, a final gathering of matter before the long fade into cosmic solitude. Within it, stars orbit, planets circle, and time continues to pass, even as the rest of the universe slips away beyond perception. This future loneliness is not an error or a tragedy in the universe's design. It is a consequence of the same physical laws that allowed stars, galaxies, and life to exist in the first place. Expansion created space for structure to form. Gravity gathered matter into galaxies. Dark energy now ensures that those structures will eventually be separated beyond communication. The universe is not cruel. It is consistent. It follows its rules without regard for observers, and yet those rules produce outcomes that resonate deeply with human emotions: loss, beauty, finitude, and awe. By imagining this distant future, we gain a clearer view of our present. We live at a time when the universe is still open to observation, when its vastness is visible, when its history is written across the sky. This will not always be true. One day, Milkdromeda will drift alone through an expanding void, carrying within it the last visible trace of a once crowded cosmos. And in that quiet, isolated future, the universe will not feel infinite. It will feel intimate, bounded, and profoundly silent. A place where the greatest mystery is not what lies beyond the horizon, but the fact that there ever was a horizon at all. Seen from the distant future we have just imagined, humanity barely registers at all. A brief flicker in cosmic time, a thin layer of chemistry on the surface of one small planet, orbiting one ordinary star, inside one galaxy that itself was never meant to last. From that scale, it would be easy to conclude that humans are insignificant, that our thoughts, fears, and aspirations dissolve into irrelevance against the backdrop of billions of years and trillions of stars. And yet, this conclusion misses the most important part of the story. Size is not the same as meaning. Duration is not the same as value. The universe does not grant significance based on mass or longevity. What makes humanity remarkable is not how large we are or how long we persist, but the fact that a small, temporary arrangement of matter has learned to look outward and understand the whole. We are tiny, yes, but we are also aware. We are the part of the universe that has become conscious of itself. This realization reframes everything we have explored. The collision between the Milky Way and Andromeda is not a cosmic threat looming over our future. It is a natural process, one chapter in a story that began long before Earth formed and will continue long after it is gone. Galaxies collide. Stars are born and die. Structures assemble and dissolve. None of this is directed at us. None of it is personal. And that, paradoxically, is what makes it profound. We are not the target of the universe's events. We are witnesses to them. And witnesses matter, because without them, there is no meaning at all. Only motion. Consider where we find ourselves in time. We live during what could be called the observable age of the universe, an era when the night sky still reveals its depth, when distant galaxies are visible, when the afterglow of the Big Bang still washes faintly across space, when the laws of physics can be tested not just locally, but across billions of light years. This window is temporary. In the far future, as we've seen, expansion will erase the evidence. The universe will grow quiet and isolated. Observers then, no matter how intelligent, will inherit a cosmos stripped of its history. They may never know the universe had a beginning. They may never see another galaxy. They may never reconstruct the vast story we can read today almost effortlessly, simply by looking up with the right instruments. That alone places us in a rare position, not because we are special by design, but because we exist at a fortunate moment. We are alive when the universe is still legible, and that legibility is a gift. It allows us to ask questions that will someday be unanswerable. It allows us to trace the origins of stars, galaxies, and even ourselves back to the earliest moments of cosmic history. When we study the future collision of galaxies, we are not indulging in idle speculation. We are using the present clarity of the universe to understand its long-term behavior. We are peering across billions of years with confidence, not because we are guessing, but because the laws that govern matter and energy are consistent. Gravity behaves the same tomorrow as it did yesterday. Light carries information faithfully across vast distances. Space expands according to rules we can measure. From these simple principles, entire futures unfold. That is one of the quiet miracles of science. With a finite mind and a finite lifespan, a human can predict the fate of structures millions of times larger than themselves, unfolding across timescales millions of times longer than their own lives. The impending merger of galaxies illustrates this perfectly. At first glance, it feels apocalyptic. Two massive systems on a collision course. But as we followed the process step by step, that impression dissolved. There is no sudden annihilation, no moment where everything ends. Instead, there is transformation. Disks become ellipses. Order becomes chaos, then settles into a new order. Star formation flares, then fades. Black holes merge silently, reshaping space-time without spectacle. What survives is not the original form, but the accumulated history. Matter is conserved. Energy is redistributed. Nothing is wasted. Everything is rearranged. This is a theme that repeats at every scale of the universe. Stars do not vanish when they die. They seed the cosmos with heavier elements. Galaxies do not disappear when they collide. They become something else. Even Earth, when it eventually becomes uninhabitable, will not be destroyed. It will continue to orbit the Sun's remnant, carrying the chemical record of oceans, life, and continents long after biology has ceased. The universe does not erase. It transforms. Understanding this softens our relationship with endings. Human culture often treats endings as failures, as losses without remainder. But cosmic history tells a different story. Endings are transitions. They are boundaries between phases, not terminations of existence. The Milky Way will end, but only in the sense that childhood ends when adulthood begins. Something is lost, yes, but something else takes its place. Milkdromeda is not a tombstone. It is an inheritance. This perspective invites a quieter kind of humility, not the humility of insignificance, but the humility of participation. We are part of processes that began before us and will continue after us. We do not control them. We do not stand apart from them. We are embedded within them. And yet, within that embeddedness, consciousness arises. Matter becomes aware of matter. Atoms arrange themselves into brains capable of modeling galaxies, black holes, and the expansion of space itself. That fact alone defies easy explanation. It suggests that meaning in the universe is not imposed from outside, but emerges from within, wherever complexity and awareness intersect. When humans look up at the sky and trace the future of galaxies, the universe is not indifferent in that moment. It is being understood. And understanding changes the nature of existence, even if it does not change its outcome. The collision between galaxies will happen whether or not anyone is watching, but the story of that collision only exists because someone can follow it, narrate it, and place it within a larger context of cause and consequence. This is the quiet power of knowledge. It does not grant control over cosmic events, but it grants coherence. It turns randomness into pattern, fear into comprehension, mystery into structured wonder. This is why science, at its best, is not cold or detached. It is deeply human. It allows us to confront vastness without being crushed by it, to face finitude without despair, to acknowledge our smallness without surrendering our sense of meaning. The calm tone of cosmic documentaries reflects this balance, not urgency, not alarm, just clarity, patience, and respect for scale. There is also a moral dimension hidden within this cosmic view. Knowing that we live in a brief, privileged window places responsibility on us, not responsibility to save the universe. It does not need saving, but responsibility to preserve knowledge, curiosity, and perspective. If future observers may be cut off from the wider cosmos, then what we learn now matters more than it seems. The maps we draw, the theories we test, the stories we tell, these are fragile things. They exist only as long as civilizations remember and transmit them. In that sense, understanding the universe is not just an intellectual pursuit. It is an act of stewardship. We are caretakers of a moment when the universe can still be known. And within our own lives, the same lesson applies. Human lives are short. Civilizations are fragile. Cultures rise and fall far faster than galaxies ever change. But impermanence does not negate meaning. It defines it. A sunset is beautiful precisely because it fades. A melody moves us because it ends. The universe's grand transformations do not diminish our experiences. They contextualize them. They remind us that meaning is not measured by duration, but by depth. To live in a universe where galaxies collide and black holes merge is not to live under constant threat. It is to live inside a dynamic, evolving system that has room for complexity, life, and thought. The calm narration of cosmic history does not lull us into passivity. It invites us into perspective. It encourages us to step back from immediate anxieties and recognize the longer arcs at play. In those arcs, humanity is not the center, but neither is it irrelevant. We are a thread woven into a tapestry far larger than ourselves, capable of recognizing the pattern even if we cannot see the entire cloth. When the Milky Way and Andromeda finally merge, there will be no witnesses from Earth. Our planet will already be silent. But that does not make the story meaningless. We are the witnesses now. We are alive at the moment when this future can be predicted, visualized, and understood. That understanding is not inherited automatically. It is built slowly, generation by generation, through curiosity, skepticism, imagination, and patience. In learning about the fate of galaxies, we are also learning how to think about our own fate, not as something separate from the universe, but as an expression of it. In the end, the universe does not ask us to be permanent. It asks us to be aware. And for a brief moment in cosmic time, we are. That may be the most extraordinary collision of all. Not galaxies meeting in space, but matter and meaning intersecting in a mind that can look up, comprehend the vastness above, and find calm rather than terror in its immensity.